Hello everyone, welcome to today's class. This is Teacher Simon taking you through AS Chemistry paper 9701/22 for May-June 2025, and this is part 2 for questions 4 to 5. Question 4 part A. Propanoic acid reacts with reducing agent Q to produce propan 1O. Roman 1 suggests the formula of the reducing agent Q. This one has to be lithium, aluminium, tetrahydride. We have two reducing agents. There is also sodium hydroxide, or you can say sodium boron tetrahydride. But this one here does not reduce carboxylic acids, but instead it reduces what? Aldehydes or the ketones to primary alcohols and secondary alcohols respectively. It is only lithium aluminium tetrahydride that can reduce carboxylic acids to alcohols. Roman 2. Complete the equation to show the reduction of propanoic acid to propan 1O. Use H here to represent one atom of hydrogen to form Q. Now, here, first of all, I will write this one, which is CH3, CH2, CH2OH. Okay, these ones were two oxygens, but here we are seeing one oxygen. Now, one oxygen added to the hydrogens, then we get water. So here I will put plus what? Water. You see that? Now let's check how many hydrogens do we have here. These ones are 3, then 5, 6. Are we there? Come to this other side. This is 3, 5, 7, then 8. Okay? If those are 8, then we also have 2 here, that will be 10. Those are 10 hydrogens. So here we are having 3 plus 2, 5, 6. So to make 10 hydrogens, that means I will put a 4 here. Remember, oxygens are 2 here, and then 1 here and 1 here. So we only needed to balance the what? The hydrogens. Now I don't need to put a number here, because when we don't put a number, you just know that there is a 1, okay? But no need to do that. Then part B, propan 1O is converted to compound T in a 3-step synthesis. In step 1, thionyl chloride is added to propan 1O to produce compound E. That is a substitution reaction, okay? So here we are going to find, you are going to get CH3. This E here is going to be CH3, CH2, then CH2. Remember, we are having this one here, so we are going to replace this one with a Cl. You see that? Let me show you that in the book. If we go to alcohols, that is chapter 17 here. In alcohols, when they react with, it's a substitution reaction. When they react with PCl5, they react with PCl3 and then thionyl chloride. You can see sulfur dioxide here can also be used to substitute a chlorine. It is sulfur dichloride, okay? Dichloride oxide, or we call it the thionyl chloride. It is here. The reaction is here. I think you can see. So we substitute the OH here by the Cl. Then you get HCl and then this sulfur dioxide. Another reaction is when you react it with what? This phosphorus pentachloride. When you react it with phosphorus pentachloride, you still get that halogenoalkane, then HCl, and then POCl3. But when you use PCl3, then you will need to add some heat, okay? But here, it is just done under room what? Temperature. Okay, now let's go back. So that means this is what we are going to get. Then in step 2, E reacts with a suitable reagent to produce butanylnitrile. So butanylnitrile is going to be CH3, CH2, CH2, then CN, a nitrile. So we are adding there a cyanide, okay? A cyanide ion. And this one can come from KCN or sodium what? Cyanide. Okay, those are the reagents which we can have there. Then in step 3, butanylnitrile is heated with sodium hydroxide aqueous. This is hydrolysis, okay? Alkali hydrolysis. Alkali hydrolysis. We can say alkaline, maybe. I think that one is better. Alkaline hydrolysis. First of all, you will form a carboxylic acid. Let me show you in the book, the carboxylic acid. Then we'll react with this one here, with the sodium hydroxide, because the other one is an acid and this one is a base, is an alkali. So they are going to react and then we get a salt, okay? So if we check in carboxylic acids, we see it in chapter 17. I think that is where we are going to get it. How do we form carboxylic acid? Those acids are formed from, we must get, it is here, carboxylic acids. Reactions that form carboxylic acids, do you see? Carboxylic acids are also made from nitriles. And they are saying that when a nitrile is refluxed with dilute hydrochloric acid, that is acid hydrolysis, okay? Hydrolysis occurs. And this bond here, this group here at the end of the hydrocarbon chain is converted to the COOH, forming a carboxylic what? Acid. You see that? And then the salt here, ammonium chloride. This question here for ammonium chloride is not, because they can ask you of that, and it is called inorganic salt that is formed there. That is ammonium what? Chloride. Now, you see that here we are getting a carboxylic what? Acid. But when we use sodium hydroxide aqueous, okay, we are going to have sodium here attaching itself here. This carboxylic acid you have formed is now going to react with the sodium hydroxide and you form a salt, okay? A salt here instead of the acid. You get that? Okay, now let's go back. Now, Roman 1 here, they are saying name the type of reaction that occurs in step 1. So here we see that the chlorine is substituting the OH. So that is what we call substitution reaction. Substitution reaction. And then next, they are saying Roman to identify the reagent and conditions required in step 2. Step 2, we are seeing butane nitrile. So we shall need, let's say potassium cyanide, okay, in ethanol, okay, because if you are just using hydrogen cyanide, this one we use it, let's say when we are forming, when we are reacting, let's say these carbonyls with, let's say hydrogen cyanide in here, and then we put trace amounts of sodium, let's say cyanide or potassium cyanide, we form what we call hydroxy nitriles. So the product is going to be the CH3, then OH, then maybe CH3 here, and then we shall have a what? A nitrile here, hydroxy nitrile. You see that? So for this case, what we are forming here, we must have ethanol in there, and then we see that the OH that is formed is actually substituted with, this Cl here is substituted with the Cn. And of course, we shall put heat and heat, because heat actually speeds up the rate of a chemical reaction. Then Roman 3, construct an equation to describe the reaction of butane nitrile with sodium hydroxide. Now, when you check in this book here, we saw that we are having only HCl, but we are not seeing what? Sodium hydroxide, right? So you see what is here. Now, I'm going to write my equation this way. I'm going to say maybe this one here, then plus I'll put sodium hydroxide here. Aqueous, I'll add there the water. You see that? Water. Then I get here the Na, then plus. Instead of writing NH4Cl, because the Cl here comes from the HCl, I'm going to take the OH and then I attach it on this. Then it will give me ammonium hydroxide. You see that? Or ammonia. So I can have CH3, CH2, CH2. There's also CN, okay? CN. Then we can add sodium hydroxide and then water. Then we can have CH3, CH2, CH2, then COO, then Na. And then I said that here we are supposed to add on what? Ammonia. Okay. Ammonium hydroxide. Now what is left for us to do is to balance. So if we try to balance this one here, we are seeing 2 oxygens here, and yet here there are 3. So what does that imply? I think I can put a 2 here, just like it was in the book. You see here we had 2 molecules of water, okay? So I'll come here and I also put 2 molecules of what? Of water. Now, oxygens are 2 plus 1, those are 3, not so? 1 here and then 3. What else? Then hydrogens, how many are they? These are 4, then 5, 6, 7, 8, 9, then 12. Okay? Those are 12. Then we come to this side. These are 5, then 7, 8, and then 12. The rest are okay. So balanced. It has to be like that. Then Roman 4, they are saying, name the type of reaction that occurs in step 3. In step 3, it is hydrolysis. Okay? Hydrolysis. But I can say alkali hydrolysis. Alkaline hydrolysis. Okay? So even if you just hydrolysis, they give you, because we have acid hydrolysis and then alkaline hydrolysis. Part C, compounds A, B, and C belong to the alcohol homologous series. Each molecule of A, B, and C contains 4 saturated carbon atoms. Roman 1, identify the type of hybridization shown in the saturated carbon atoms of all alcohols. Of course, this one is going to be sp what? sp3. sp3 comes from here. You have a carbon. Carbon has 4 electrons in the outermost shell, right? So we are having, remember carbon is in position 6, not so? So we have 1s2, 2s2, 2p2. Then we are having 2 in the 2s. And then 2p, remember there are 3 what? Orbitals in the 2p. So you have 1, 2. Those are the ones. Now what happens is that an electron is excited from here to come there. Then when an electron is excited from here to come there, then you are going to have a mixture of these orbitals. You see that? Then they are going to become degenerate. Degenerate orbitals are ones which have the same what? Energy. Now, if I have another carbon atom which also has the same number of electrons in here, so one carbon is here, then another one is there. So what is going to happen, remember, it is like this. There is maybe a hydrogen, and a hydrogen, then there's a carbon here. So I can get a hydrogen here, then each of them is having 3 hydrogens, right? So we are having a hydrogen and also a hydrogen here. Same hydrogen and then a hydrogen here. Those are the 3 hydrogens. Then that is for one carbon. And of course, this one is also having more that are continuing, okay? Now, these 2 are forming a bond in between them. This is the one here. You see that? So, in there, when they form this bond, you look at the sigma bonds that are formed. So, all of them have been utilized. We are seeing 1 from the 2s and then 3 from the 2p. So that's why we write sp3, 1 from the S, then 3 from the P. Then if it comes to, let's say, a double bond, when there is a double bond, these two are occupied, you have something like this, like that. And then they all have the hydrogen, then another one here. So even this one has, and then this one has. Then there is a bond formed in between the two, because here there is one sigma bond and then one pi bond. Then this other one, which is remaining here, so they do sideway overlap of orbitals. So you look at those sigma bonds which are formed before the sideway overlap. So there is this one is one sigma bond, the second one is here, the third one is here. So there is one for S. Then P, there are two of them because we are seeing here and then here. You get it? Before this one here. Now it becomes sp2 for the alkenes. You see that? So that's what we have. But for saturated carbon atoms, you should know that we are having how many? The type of hybridization is sp3. Then next, here they are saying, identify the gas produced when sodium is added to separate samples of alcohol. So if we have, let's say, maybe CH3 OH, then you add their sodium, you are going to have CH3. We call these ones sodium alkoxides, okay? Sodium alkoxides. Then plus a hydrogen is driven away from there. So the gas there is what? Hydrogen. So identify the gas, then I can put hydrogen. So whether you write it as H2 gas, it is okay. They said identify. They didn't say write the formula of the gas. They didn't say write the name. So when they say identify, you can give the formula or the name. You get that? Now, what else do we have? Deduce the role of sodium when it reacts with alcohols. Now, you can see here that this one has lost a hydrogen. And we can see that sodium, even here, it has a plus. This one has a minus, okay? Because sodium, when it reacts in there, it loses electrons. So because it has lost electrons and it has given them out to this oxygen here, that means the one that has received electrons is being reduced. So therefore, sodium becomes a reducing what? Agent. Sodium here is a reducing agent. So for it actually gets oxidized because it has lost electrons. A reducing agent reacts by getting oxidized, by losing electrons. You get it? And then an oxidizing agent reacts by receiving electrons. So in other words, it gets reduced in return. That is the oxidizing agent. Then part D, this table here shows the results of two tests on separate samples A, B, and C. Then we are seeing that for A, heat under reflux using acidified potassium dichromate, it remains orange. Now, if it remains orange, remember all of these ones are alcohols. It must be a tertiary alcohol. Tertiary alcohols do not undergo oxidation. Then we are also seeing warm with alkaline iodine, okay? Warm with alkaline iodine. Now, alkaline iodine for alcohols, for a positive test, we must have CH3, C, then OH, then H here. Maybe I can put it there. And then there is any other group that comes forth. But so long as there is this CH3. So what is going to happen is they first oxidize this one to a ketone. So you have CH3, C, this. So that group is created. Then after this CH3, the hydrogens on the CH3 are replaced by the iodides. And then after hydrolysis takes place, it is broken down, and then we see iodomethane, the triiodomethane. So this group must be there, must be present for a positive test. Okay, for a positive test, let me put it actually here. For a positive test with alkaline what? Iodine. Now, remains orange, then we have to say that this is a tertiary what? Alcohol. Because for them, they never get what? Oxidized. Are we there? So that means here, and how many carbons do we see? They said that these ones have 4 saturated carbon atoms. So a tertiary alcohol is therefore going to have this structure, CH3. First put a carbon here, then the OH here. That means we should have a CH3 here, and then another CH3 here. Okay, this is the one we are going to have here for A. You see that? Now, this one it doesn't have this group here. Yes, you can see the CH3, then COH, but it doesn't have the hydrogen attached to that one, to this carbon here with the OH. You see that? So that means it cannot give you a positive test with alkaline iodine. Are we there? So actually that is my structure. So I can say this is CH3, COH, then CH3, and then down here I can have my CH3. So just like that. And then when we look at B, orange to green, that means we can have a secondary alcohol. It can be oxidized. If you oxidize a secondary alcohol, you can get a ketone. If you oxidize a primary alcohol, then you can get analdehyde and then later a carboxylic acid. So that means here we can have a secondary alcohol. Okay, we can have a secondary alcohol or a primary alcohol. The same with this one here. Okay. Now, after that, there is no visible change. Let's check the structures which are going to be here. We can have CH3. First of all, they said that this one doesn't have any visible change. So there is no CH3, CHOH. That group is not there. This group is not there. So I'm going to draw something like this. And I say maybe this is CH3, then CH2, then let's say there are 4 carbons, then CH2OH. This one can be oxidized to carboxylic acid here, orange to green now, okay? And then here there is a pale yellow. That means this is triiodomethane. So that means when I'm drawing, let me take off this one, by the way. This is CH3 like that. CH, then I3, triiodomethane. Now, I must have a CH3, CHOH group for me to have this pale yellow. Are we there? Now let's put here another group. This is, how many carbons are they supposed to be? They have to be 4. So I can put a CH2 and then a CH3. Now you can see that this one has this group here. So it can give that. Now let's continue. What are they saying? So this one might belong here, and then this one here. Another one where we can have, let's say this one can belong to C, okay? This one can be C. And then this one, I can take this CH3 here, and then I take it here. So when I do so, I will get this CH3, then C, then CH3 down here. These are 2 hydrogens. One will rearrange and then comes to this one here. That's why it is giving us this CH3. Now that means here we shall remain with 1 hydrogen and then CH2OH. This one also will not give a visible change here. So this simply implies that these 2, B, can be this one or it can be that one. You see that? Then C can be this one here. Now, let's see. They are saying deduce the possible name for B. The possible name for B, it can be how many? 1, 2, 3, 4. That is butan 1O. You see that? Butan 1O. Because this OH can also move to the second carbon, and then we say butan 2O. Then here, this is a propano. Then this is a methyl group there. Or I can say 2-methyl propan 1O. Propan 1O. But again, we don't have 1-methyl, because if the methyl group then is attached to this one, then we are going to have, that will be butan 2O. You see that? So you might find when they haven't written something like this, 2-methyl, and they just write methyl propan 1O. Okay, then deduce the identity of C. C is here. That is 1, 2, 3, 4. That is butan 2O. Can say 1, then 2. So the OH is on the second one here. It has to be butan 2O. Like that. Question 5. The structure of vitamin C is shown in this figure here. And they are saying part A, deduce the empirical formula of vitamin C. Remember, empirical formula shows the simplest whole number ratio of atoms in a given molecule, right? So that means I'll use the molecular formula, okay? Then I simplify the molecular formula to get the empirical formula. So here we are going to have a carbon first of all. A carbon here, a carbon here, a carbon here, a carbon here, a carbon here. Okay, carbon must have 4 bonds, so that means the hidden ones are hydrogens here. This one is a skeletal formula. So for a skeletal formula, they hide the carbons and also the hydrogens that are directly connected to the carbons. The hydrogens here are connected to the oxygens. Those ones are left. It's a functional group there. But the ones that are connected to the carbon are always hidden. Okay. Now these ones are 3 bonds in here. We must have a 1 bond here. Then what else? Carbon here must have a hydrogen to make this one 4. These ones are 2, 3, and 4. 2, 3, 4. Yeah. So we shall have those ones there. So how many carbons do we see? Carbons, we are seeing carbons, then hydrogens, and then oxygens. Carbons are 1, 2, 3, 4, 5, 6. Okay, so we shall put a 6 here. And then hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. Those are 8. And then all oxygens, 1, 2, 3, 4, 5, 6. So we are going to have a 6 here. Then we can divide all through by the highest common factor. For 6 and 8, of course, it is going to be a 2. Then we shall have C3, then hydrogen 4, then oxygen 3. Divide by 2, 3. Divide by 2, 4. Divide by 2, 3. Okay, that is that. Then we continue, we come to part B. They are saying the mass of vitamin C present in 150 grams of lemon is found in an experiment. Okay, and then stage 1, all the vitamin C in 150 grams of lemon is extracted and dissolved in water to make 100 cubic centimeters of solution L. And then they are saying stage 2, a 25.0 cubic centimeter sample of solution L is titrated with this 5 times 10 to power negative 3 moles per liter of iodine solution. And then we are given the equation here. You can see that this one was, this one is an alkene, but then here it is no longer there. And then these are alcohols. And then here you are seeing what? A ketone, a ketone. So that means this one has been oxidized, right? But these ones remain. Okay. Then they are saying exactly 36.65 cubic centimeters of iodine solution reacts with 25 cubic centimeters sample of solution L. Now, this means that this iodine solution is actually a standard solution, because a standard solution is the one that has got a known concentration and also the volume that it uses to react. You see that? Then the MR, the relative molecular mass of vitamin C, is 176. And then Roman 1, they are saying calculate the amount in moles of iodine solution added in the titration. So first of all, I always show the calculations in mole concept here using first principles. So when you check this one here, just this part here, this one means these moles are in a liter. A liter is the same as 1 decimeter cubed, is the same as 1,000 cubic centimeters. So we can say 1,000 cubic centimeters, okay, of solution contain this 5.00 times 10 to power negative 3 moles of what? Iodine. You see that? Then how about the 36.65 which reacted? How about the 36.65 cubic centimeters of solution? Okay, so this one will contain 36.65, then times this 5 times 10 to power negative 3, then you divide by what? 1,000. Now, usually, when you are getting the moles, you are going to just get this volume. The volume, which is here, has to be in liters. So you divide by 1,000, because 1 liter is equivalent to 1,000 cubic centimeters. So you divide this one by 1,000, then times the moles that you're having here, the molality, okay? Then the concentration for that case, and then you get the answer. So what do we get here? We have 36.65 times 5 times 10, then to power negative 3, and then down here we have, of course, 1,000. Then we get 1.8325. 1.8325. It was an exact number. I can write all of these ones here. Okay. Then next, Roman 2, use your answer to part B, Roman 1, to calculate the percentage of the mass of vitamin C present in 150.0 grams of lemon. So that means we need to find a mass present, then that mass divided by this total mass times 100. That one will give us the what? The percentage of vitamin C. And then here they are saying, if you are unable to calculate the value of the amount of moles of iodine in B1, use this value here. So this one is given for people who have failed to do the first part that they have given you. You get it? But for us, we have gotten it. So what do we need to do? We need to come to this one here. After getting the moles of this standard solution used here, you come to the stoichiometric equation, okay? So, and we can see that it is 1 to 1. One molecule of iodine is reacting with one molecule of vitamin C, okay, to give us this one here. So this simply implies that the moles, okay, the moles of vitamin C that reacted, vitamin C that reacted will be equal to the moles of aqueous iodine that reacted, which is actually 1.8325, then times 10 to power negative what? 4. Okay? After that, remember we need to get the mass. So these moles here are contained in what? These moles are contained in 25 cubic centimeters. Okay? So we shall come here and we say 25 cubic centimeters of solution, okay, contain this one, this solution here contains this 1.83, then times 10 to the power of negative what? 4. Then how about 100? Because this 25 cubic centimeter aliquot was gotten from 100 cubic centimeters here, right? So how about 100? Not 1,000, it's 100 cubic centimeters. will contain, so this one will contain, you say 100 times 1.8325 times 10 to the power negative 4. Then we are dividing by what? 25. Now, 100 divided by 25 is actually 4. You might find when they have gotten this one here and then they multiply it by 4. You see that? Then after that, those are the moles which we are going to have of vitamin what? Vitamin C. Then from there, we are going to get now the mass. So the mass, you know that moles are equivalent to mass, then out of what? MR. So that means if I want mass, then I will get the moles times the MR. Not so? So I'll get our mass here, which is going to be what we have gotten here. Okay. Let me even just duplicate it just like this. Then times the MR. MR was given as 176. Yes, it is here. 176. Okay. Then what we get from here, what is it, by the way? 100 times 8325 times 10 to the power of negative 4, then times 176, we shall divide by 25, we get 0.1290008 grams. Okay, then the percentage by mass, percentage of vitamin C is going to be this one, 0.129008. We divide by the 150, then times 100. Then what do we get? So the answer we have here, we shall multiply it by 100, then we shall divide by 150. That is 0.086. 0.086%. And by the way, this is 150. Then Roman 2, they are saying the progress of the reaction of vitamin C with iodine to produce M is monitored using the infrared spectroscopy. Here we are looking at the absorptions at given ranges, of course, to tell us which functional groups are present. Okay, so table 5.1 indicates the presence of some absorptions in the infrared spectrum of vitamin C. And they are saying here that we have to complete that table to predict which of these absorptions, if any, are present in infrared spectrum of M. For vitamin C, they are giving us 1500 to 1680. This is the one here which represents what? An alkene. Okay, an alkene. So if we go back and we check for vitamin C here, there is an alkene here, carbon to carbon double bond, you see? So then they put a tick. Then 2850, 2950. 2850, you can see it here. And then this one corresponds to an alkane. Okay. Now, when we check here, to an alkane, so there is carbon here, there is a hydrogen. You see that? Carbon to hydrogen is there. There's also here carbon to hydrogen. There's also here carbon here, and then a hydrogen here. So there is also what? Alkanes are also there. So that absorption will be given. You get it? Now, for M, do we also see? Actually, let me finish this one straight away. There is also that CH. This part here, the way it is also here. Do you see that? Now, that means this one is also going to give the absorption for an alkane. You see? So there is a tick for an alkane. I'll come here, and then I also put this one for an alkane. But coming back to this one here, for M, remember this one was for the alkene. Not so? Here, we're looking at the alkene. But when we look at M, if you come back here and you check M, there is no carbon to carbon double bond here. So that means this absorption here, it is going to be there for vitamin C, but it is not going to be there for M. I can put a cross, I can put a dash, I can even just leave it blank, just like that, okay? But let me just put a what? A cross. Okay, then let's go to this one. Of course, this is for the hydroxyl, for the alcohol. So OH here, 3, 2 to this one here. When we go to M, okay, when we go to M, you can see that we are having OH and also OH here, just as this is, and this one here. So that means it is going to give us that, that kind of what? Absorption. So even here, there will be a tick there. Okay. So this has been it for this part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next videos.